Swayam Prabha. Digital India. Educated India.
Hello friends, in the last lecture we have covered the basic theory of electronics. Now on we will move to our experimental modules. So in the first lecture we will cover the stepper motor details and its control, how to achieve it. So let us start. So and we will see in the lab we will see three varieties of the control, starting with the basic manual control, then Arduino based control and lab view based control. So I am Anjali Kulkarni from the Center for Mechatronics, Principal Research Engineer at IIT Kanpur. Stepper motor. It is an electromagnetic incremental actuator which converts electrical pulse to mechanical movement. It is a brushless synchronous electric motor that can divide a full rotation into number of steps. The motor's position can be controlled accurately without any feedback mechanism. So in the picture you see there are various sizes of stepper motors. So the size decides the torque, or the torque decides the size. So higher the torque, bigger the size of the motor. There are various advantages of stepper motors. The motor has full torque at standstill. This is a very handy technique which is normally proves benefits that whenever a motor fails it loses the torque or the connection, but with the stepper motor this is not so. Even if the motor is off, it provides the full torque. Then it can be precisely positioned with repeatability. The accuracy of the step is around 3 to 5% and the error is non-cumulative. Excellent response to starting, stopping and reversing. It has reliable operation as no contact brushes in the motor are used. This also gives us a long life of the motor, and the control which we use is an open loop and very cost effective. Low speed synchronous rotation with a load that is directly coupled to the shaft is possible, which is otherwise not possible with the DC motors. A wide range of rotational speeds can be realized as the speed is proportional to the frequency of the input pulses. There are various applications of the stepper motors. In industrial machines it is used as an automotive gauges and machine tooling, automated production equipment. In security fields, new surveillance products are designed using stepper motor for the security industry. In medical industry it is used inside medical scanners, samplers, digital dental photography, fluid pumps, respirators and blood analysis machinery. In consumer electronics it is very widely used. Most commonly it is used in cameras for automatic digital camera focus and zoom functions, and in printers etc. And there are many other usage. There are two basic windings found in the mechanical arrangements of these motors. These are called unipolar and bipolar. So there is a printing mistake here. A unipolar stepper motor has one winding with center tap per phase. Magnetic pole can be reversed without switching the direction of current. The commutation circuit hence is simple. A single transistor per each phase is used, and in bipolar winding there is single winding with 2 leads per phase and no lead is common. The current in a winding needs to be reversed in order to reverse a magnetic pole. Hence the drive circuit becomes complicated, and typically H-bridge circuits are used for bipolar winding arrangements. Typical operation of permanent magnet stepper motor can be shown with respect to these figures. So there are 4 phases which are energized in a proper sequence. to advance the rotor in a particular direction. In figure A, you see this is a rotor and this is a stator. So, there are poles and two poles at a time they are switched on. So, here you can see in this figure A, stator pole A and C is switched on, the rotor is in this position, and with the application of the power to A and C, there is a torque that gets generated, so that N1 gets aligned to this D pole, and in the B, so you have seen this clockwise rotation that has happened because of the supply given to A and C. And in the next figure, the supply is changed from A to C to B to D. So, consequently the change in magnetic fields take place and that causes a deflection and rotor moves. So, that gives a continued clockwise rotation. So, for ease of simplicity or understanding the mechanism, here we present an open architecture of the stepper motor. So, these are normally used, these windings are unipolar windings. There are 8 poles on the stator and this is a permanent magnet rotor which had got 50 poles on rotor. So, we need 200 pulses, that is 50 into 4 pulses to make one rotation. So, this 200 pulses result in 1.8 degree rotation per pulse. Stepper motor performance depends on the drive circuit. Torque curves may be extended to greater speeds if the stator poles can be reversed more quickly. The limiting factor in doing so is the winding inductance. To overcome the inductance and switch the windings quickly, one must increase the drive voltage within the permissible limit to withstand current that these high voltages may otherwise induce. There are different driving strategies. One is called as full step drive, 2 phases on, as we have seen in the last figure. This is the usual method for full step driving the motor. The motor will have full rated torque in this configuration. There is another half stepping mode wherein single phase is on at a time. When half stepping, the drive alternates between 2 phases on and a single phase on. This increases the angular resolution, but the motor has less torque, which is approximately 70% of its full torque. This may be mitigated by increasing the current in the active winding to compensate. There is another driving strategy that is called as micro stepping. It is often sine cosine micro stepping, in which the winding current approximates a sinusoidal AC waveform. The functioning becomes very smooth and resolution is further increased. Nowadays, there are hybrid stepper motors available in the market. The one common in use is the M drive 17 plus motion control. This is a NEMA size 17 high torque motor with 1.8 degree stepper motor integrated with a micro stepping driver, and a full featured programmable motion control is available with this. That is why it is called a hybrid motor. This has got RS422 or 485 communication. So, this motor can be programmed using serial communication port. The input voltage ranges from plus 12 volt to plus 48 volt. So, this can be used in variable torque applications, and the holding torque is about 52.9 Newton centimeter, and there are IO lines up to 8 general purpose points are provided that provide the robust programming with input filtering. This has inbuilt step direction IOs for electronic gearing. So, one can further gear the motor to have to achieve micro stepping. So, this is a motor which is a standalone, having standalone controls for high end industrial applications. So, once these motors are programmed, so one can have a standalone control of the machines. Coming to our experimental part, So, this figure depicts a general control scheme where we need a clock frequency, a sequence generator and a amplifier. So, here is a power driving amplifier, then this is a oscillator which generates clock, and these are the switches which are used to power on the coils which are made on or off depending on the sequencer's output. In the laboratory, we will be performing experiments with different control strategies. The basic scheme remains the same, but we will be using advanced control strategies. Like we will begin with the manual control, wherein the oscillator that is 555 timer based will generate a clock frequency, and we will have a simple control without any feedback. Then we will move to a little bit complicated control which will be Arduino based, wherein we can have input and output facility as well, and we can control many motors with this. Then there is a variety of motion control card based control of the stepper motors. For that we need to have a software platform. So, here we will be using LabVIEW platform. LabVIEW stands for Laboratory Virtual Engineering Workbench. So, our first experiment will be about manual control using clock signal. This is a simplest and low cost circuit mainly used in low power applications. 555 timers IC based clock circuit is used. This 555 timer is configured in a unstable multivibrator mode, and there is a potentiometer provided which will change the clock frequency in a limited range. The frequency of the clock is dependent on the RC circuit. The formula is like this: 1.45 divided by RA plus 2 RB into C. So, this is the timing circuit, and JK flip flop and or based sequence generator is used to have sequencing in proper manner, so that we have continuous operation of the stepper motor. So, here is the sequencer, this is the sequencer, this is a power drive circuit, and here we are using 4 MOSFETs as our drive for each phase. So, here the clock is fed to the JK flip flop and OR circuit is used, and these 4 outputs Q1 and Q1 bar and Q2 and Q2 bar are fed to the MOSFETs as the input gate control. So, whenever these are high, these MOSFETs, so Q and Q bar always, Q1 and Q1 bar will be always in opposite sign. So, if Q1 is high, Q1 bar will be low. Similarly, Q2 and Q2 bar are in opposite polarity. Either if one is high, the other will be low, or this will be low, then this will be high. So, we will get a proper sequence, and phases will be on, and stator and rotor, they will change their rotor will rotate in a particular fashion. In the experiment, what we will do, we will select the direction bit, and for that particular direction bit we will vary the clock frequency, study the waveforms at different test points in the circuit using oscilloscope at 555 timer output, sequencer outputs and MOSFET output. So, here we will basically learn also the use of oscilloscope as the measuring equipment. The second control is derived around the Arduino microcontroller. So, you will be learning microcontroller theory details in another talk. Here I will just show you the block diagram. This Arduino controller is here. Power supply in the form of battery or power supply will be used. There is a on off switch, and this is a easy control drive, easy drive. So, this is the driver which is used to supply the current to the phases of the motor. So, this is the functional block diagram of easy drive. Motor's coils are connected at this point. enable is used, and step input, that is the clock circuit clock oscillations are derived inside the microcontroller by using a C program, wherein we will change this bit on and off with a particular delay. So, that delay can be changed so that the frequency of the clock changes. So, the features of easy driver are as follows. This has plus minus 750 milliampere and 30 volt output rating. This gives a supply voltage, the supply voltage ranges from 3 to 5.5 volt. It is a mixed fast and slow current decay modes, it works in that. This has got undervolt and over current facilities, and thermal shutdown circuitry is also provided into it. There is crossover current protection also available. Motors force wires are connected to the easy drive. A power supply is connected as given in the pin diagrams. So, C language is used to build the control program, wherein these modules are used. Pin function declaration is done, variables are declared, serial interfacing protocol is also activated, and the main loop of the function has user input acquisition, and we write low and high on pin number 2, which moves the motor in forward or reverse directions with the set delay time. The hardware will be shown to you, you will study that hardware, study the control program which will be provided in the lab, change the parameters and see the motor response. So, this is a one step higher control that compared to the manual control, wherein we will have the facility of changing the delay, changing the speed, changing the direction, or changing the number of steps that motor can move, or we can move the motor in a number of rotations also. Similarly, there can be a closed loop control wherein we can have some I/O depending on the sensors or any other signal, so that motor can be controlled. Then coming to the third control strategy, here we will be using motion control card, which is a dedicated hardware which can be plugged in the computer, and for programming that motion control card we need to have a LabVIEW based platform. So, LabVIEW is Laboratory Virtual Instrument Engineering Workbench. This is a graphical programming language that allows for instrument control, data acquisition and pre or post processing of acquired data. LabVIEW works on a data flow model in which information within a LabVIEW program called a virtual instrument flows from data sources to data sinks connected by wires. The data can be modified as it is passed from source to sink by other VIs. VIs consist of both a graphical user interface called the front panel and a code pipeline called the block diagram. So, there will be a function laboratory called as motion VIs, and these graphical icons, they provide the programming tools. So, each VI will be a function in itself, like you have to declare the access numbers, then you can set the mode to stepper or servo, then you can have different modes of operations like incremental mode or velocity mode. So, those can be available, so that with using a motion control card one can design a standalone system, a full fledged 6 to 8 degrees of freedom system can be designed use of these control cards. As I said earlier the VI has 3 main parts: the front panel, this is an interactive user interface of a VI, so named because it simulates the front panel of a physical instrument. The block or wiring diagram, it is the VI's source code constructed in LabVIEW's graphical programming language, it is the actual executable program, and there is another connector or icon module is there which connects the flow of the data. We will be using this National Instruments Measurement and Automation Explorer, which is called as MAX in short. So, NI provides Measurement and Automation Explorer (MAX), a graphical user interface to configure instrument drivers. MAX is usually installed with one of the NI applications development. It provides access to NI CAN, data acquisition, field point, GPIB, IMAC, IVI, modular instruments, motion, NI switch, executive, VI logger, VISA and VXI devices. So, here we will be using motion device. MAX is used to configure the NI's hardware and software, backup or replicate configuration data, create and edit channels, tasks, interfaces, scales and VIs, execute system diagnostics and run test panels, view devices and instruments connected to the system and update NI software if any. So, this is the hardware which we will be using. This is a motion control card which has got multi-axis control. This supports at a time 8 servo or stepper motors. I/O facility for closed loop control is available. Velocity control is also possible. Position, that is point to point control, is possible. Motion trajectories, that is triangular profile, trapezoidal profile or an S-curve profile can be programmed, and one can have pressure or force control as the feedback from sensors if they are used, and electronic gearing is also possible to achieve further accuracy. There are different family of motion cards available from National Instruments, PMAC, Delta. So, we are using specific National Instruments 7358 motion controller card. This is a combination of servo and stepper motor controller for PXI, compact PCI and PCI bus computers. This is a fully programmable motion control for up to 8 independent axes of motion. Coordinated motion is supported through multi-dimensional coordinate spaces. Each axis provides dedicated motion I/O for limit and home switches, and additional I/O for general purpose functions are also available. The external motion and digital I/O connectors on the NI7358 controller are high density 68 pin female VHDCI connectors. Then we need to use NI UMI 7774, which is a 4 axis universal motion interface as seen in figure. So, this is an interface card with which we can connect our motors to the NI motion card. Then here in the power, as a power drive, we are using MID 7604 power drive. This is a stepper and servo motor power drives. This provides reliable, easy to connect drive solutions for all NI motion controllers. This is a 4 axis stepper power drive. So, we can connect at a time 4 stepper motors to this. This provides 1.4 ampere per axis, and host PC bus power monitoring or shutdown is possible. This has got internal power supply, driver circuit, and heat sink is provided for the cooling. This inside has electronic gearing which is possible, and I/O pins are also provided on this to have the feedback or the actuation. So, this is a motor control hardware configuration. This motion control card, it sits in the host PC, and a LabVIEW platform is used for its programming. This is UMI 7764, which I was saying that as interface we have to use it, and then we are using this stepper drive and a stepper motor, and there is a RS-232 communication protocol. So, while experimenting with LabVIEW and using motion control card, we will use NI MAX that will be used to drive the stepper motor. We will use the configuration parameter settings, we will initialize the hardware, we will select the stepper mode, axis number, we will change the speed and position and study the working of stepper motor. So, in continuation with our theory to the stepper motors, today we will perform the actual experiments in which we will do 3 modes of controlling the stepper motor. So, here is a stepper motor, this is a rotor assembly on the teeth, and this is a mounting plate, this is the motor shaft, this is stator assembly, and this is the back plate for this to sit here. So, this is like this. So, this is the same motor as we are using in the setup. So, let us begin with the first module of the control and drive, wherein we are using a minimum basic hardware to control a stepper motor. As stated earlier, we are using a clock source 555 based stable multivibrator, which is generating a clock frequency, which can be seen here on the oscilloscope. Then we are feeding those clock pulses to a sequencer circuit, which is comprising of the flip flops and or gates, and the MOSFETs as the drivers, each MOSFET for one phase. So, we have 4 MOSFETs for 4 phases of the stepper motor. We are giving a 12 volt DC supply from the power source to the circuitry, and this digital circuitry uses 5 volts. So, we have a 5 volt regulator here. So, that is changing 12 volt into 5 volt DC, and motor phases are connected to the 12 volt through MOSFETs. And this is the oscilloscope, wherein we can see the time varying pulses. So, here you are seeing 2 channels. In channel 1 we have connected the clock pulses, and this is the output of the MOSFET. As earlier discussed, this MOSFET output is divided by 4 in the frequency. So, like now the clock is showing 196 hertz, and this will be divided by 4 frequency. So, in the clock circuit, this shows the output of the clock, which is showing the frequency 76 hertz, which we can change by changing this potentiometer reading, and we can have from 44 hertz onwards we can change the clock. Then there is a direction pulse here, which is set to one value through this switch, and here is a sequencer that is generating the pulses in proper sequence, and these are the MOSFETs, those are getting on and off as per the sequencer output. So, here you can see the motor is moving in particular direction with some speed, that depends on the clock. Now, I can change the clock, and you see at some point the motor stops, it does not respond to the clock pulses. So, this is because those 4 phases, those cannot turn on and off as fast as the clock pulse. So, this we can see, I will change the time base so that you can make it out. Here here it does not respond correctly. So, the switching time we can say that is around in the hundreds of microseconds for this inductive load of this motor. So, this is the simplest circuit. We can change the direction of the motor by changing the direction bit. So, this is the simplest control and drive of the stepper motor. So, herein there is no feedback and there is no control over the number of pulses, etc. So, for that we need to shift to another control strategy, wherein we will be using Arduino based control. So, here we are using Arduino Uno board to control the stepper motor. Arduino Uno is generating the clock and direction, and we are using a motor driver which is an integrated circuit here. As in contrast with 4 phase, we were using MOSFETs earlier in the manual control. Here we are using motor driver board, and we are writing a program in the sketch environment using C language. As you see, in the beginning we have declared the functions of the pin. So, pin 2 and 3 we will be using as step and direction, pin 4 and 5 for micro steppings, and enable is on 6 pin, and all these variables or functions are output type of functions. Then we are invoking open serial connection for debugging, and this is giving some display messages, and we will get the input from the keyboard as in 1 or 2 for moving the motor in a particular direction. Then if the user input is 1, we are invoking step forward default function, otherwise with 2 input the reverse step default input will be invoked. And here is the main loop which defines how the motor will move. So, we are using a direction bit as low, and for pulses from x1 to 40 less than 49 with a delay of 100 milliseconds we are generating the clock pulse. So, till 48 pulses the motor will move. This is a 7.5 degree motor, so we will need 48 pulses to move it in a single rotation. When the user input will be 2, then this reverse step default will be invoked. And here you can see, as I said earlier, in the reverse default step default we have earlier put as for x less than 97, that is for 96 pulses this motor will move with a delay of 100 milliseconds. So, we can change these parameters like number of pulses, we can make it into number of rotations, we can change the delay so that we can change the speed of the motor. So, if I give 1, the motor will move here through 48 pulses in a particular direction. Suppose if I change the delay, so if I make it 50 milliseconds, the speed will change. So, the delay is small, hence the speed will be more. So, now you can see the speed is double. So, this is how we can program the control. Now, I am giving 2 as the serial input, and the motor is now moving in the other direction through 96 pulses. So, that way it will make 2 rotations as the step resolution is of 7.5 degree. So, with Arduino Uno board we have a control over the number of speeds, number of rotations or number of pulses, and unlimited control on the speed also. After this we will move to another higher degree of sophistication, wherein we will be using motion control cards which will be supporting control of more than 4 motors or up to 8 motors, and we will be using a lab view platform for configuring the motors. Now we will move to a sophisticated control of the motor. Herein using special hardwares like motion control hardware and specially designed stepper motor drives, we can achieve a full-fledged system of containing 6 to 8 motors. So, we are using a 7358 controller which is sitting inside this computer. Then we are having a interface board again inside the computer, and this is the driver board bit 7604. So, this can supply current higher rating motors. This supports 4 motors at a time. In the first module we have seen IRF 540 MOSFET we were using as a driver for each phase, but here you see a complicated hardware is used because this provides many other features as well. And we are using all these hardware and control is devised using National Instruments LabVIEW platform, wherein we are using for demonstration purposes we are using NI motion devices measurement and automation explorer called as MAX. So, here you see this MAX configures the devices. We can see the device, this is NI motion device, particularly PCI 7350 board. Then we can do the settings, we can have 8 motors as I said earlier connected to this hardware. Those can be either stepper motors or servo motors. So, that is the flexibility of using this 7358 card. Then we can configure the axis, and here you see in the axis configuration sub module we have defined our motor is as a stepper motor. So, as I said we can use a servo motor as well. Then there are motion settings which we can perform, trajectory settings also can be done. We can have software gearing through programs. So, likewise there are controls for all 8 axes. We will be driving the motor using 1D interactive function first. We need to initialize the board. So, here we can set the parameters. We are using axis 1. Here there is a choice of all the other axes as well. We have connected this stepper motor 1.8 degree resolution stepper motor to axis 1. We can change the velocity. We are using right now 20 RPM. We can give the target position as we have applied the parameters. Now, we will start and you will see the motor is moving through 5000 pulses. So, that has made 2 rotations, full rotations and 1 half rotation. So, we have applied 2000 pulses as a target position. We will move the motor and we will see the motor will move through 1 rotation. As motor is same as 1.8 degree, then why it took 2000 pulses for making 1 rotation? Because there is a provision of gearings. Having soft gear, we can set these values by selecting the dip switches here. So, that is the beauty of this, using dedicated soft hardware for the purpose like motion drives which we are using here. So, for changing the direction we need to give the minus as position here. So, now you will see the motor is reversed through one rotation. There is another interactive mode of driving the motors. Here in 2D interaction there are different modes. Now we can drive simultaneously axis 1 and axis 2, and where you have we can have the motion in circular move or contouring mode or in a 2D straight line move. So, these are the features which we can achieve. So, we can using motion drive and the ready-made power drives for them, we can achieve a sophisticated control of 8 motors simultaneously. So, we have seen the use of max for control of the motor, and to develop a particular program we need to use National Instruments LabVIEW program platform, and therein the function library of motion functions, those will be used, that will make a complete software which will be a complicated software and can be used for 8 motors. In continuation with our experimental modules of the robotics course, today we will see introductory theory on infrared sensors. So, here you see a radio frequency spectrum starting from gamma rays, X-rays, UV to visible light to infrared and radio waves. So, here is the infrared band where the wavelength of the electromagnetic waves is between 700 nanometer to 1 millimeter, and we are concerned about this near infrared band of the wavelength 780 to 2500 nanometers. So, which is used largely in the field of robotics for detection. So, a photodiode is a PN junction device that consumes light energy to generate electric current. It is also referred as photodetector, photosensor or light detector. An infrared light emitting diode is a special purpose LED emitting infrared rays ranging from 700 nanometer to 1 millimeter wavelength, and the detector is an IR photodiode which is sensitive to IR light of the same wavelength as that emitted by the IR LED. When IR light falls on the photodiode, the resistance and the output voltage change in proportion to the magnitude of the IR light received. IR lights are usually made of gallium arsenide or aluminum gallium arsenide semiconductor technology. There are various modes of operations, mainly it is a direct mode and reflective mode. In direct mode, when the IR beam is interrupted, the sensor detects the absence of signal, and in the direct mode they are sensor and emitter, they are placed in front of each other, and in reflective or indirect mode the reflected infrared light after hitting an obstacle which falls upon IR receiver is measured. This is it is sensitive to the color and nature of obstacles. A passive IR sensor measures the thermal radiations of the objects in the IR spectrum. In robotics, we are dealing with direct mode and reflective mode IR sensors, and there are two types, digital and analog. So, what are big beam sensors? This type of sensors consist of a pair of light emitting and light detecting elements. Infrared source transmits a beam of light towards IR receiver. Once some opaque object comes in between the emitter sensor pair, the beam is broken or interrupted and the output of the detector changes. Typical applications of such sensors are intrusion detection, shaft encoder for measurement of rotation angle or rate of rotation, as you have seen these in while discussing the DC servo motors. Reflectance sensors. This type of sensors house both an IR source and an IR detector in a single housing in such a way that light from emitter LED bounces off an external object and it is reflected into a detector. Amount of light reflected into the detector depends upon the reflectivity of the surface. This principle is used in object detection, barcode decoding, surface feature detection, such as detecting features painted, taped or otherwise marked on the floor, wall tracking, etc. So, in line following robots, we will be using these kind of sensors very routinely in robotics. So, what are the applications of these IR sensors? There are two types of applications in robotics. One is called internal and external sensing. In the internal sensing, we sense the position of the robot itself by using IR sensors, and for external sensing they are used for proximity detection, range finding, line follower, object detection, motion detection, etc. Modulation and demodulation in analog sensing. Because analog sensors they are used for a large range applications, the signal, the transmitted signal is needed to be modulated so that it reaches far distance. For that purpose, a flashing light source at a particular frequency is used, and those frequencies vary from 32 kilohertz to 45 kilohertz normally. A demodulator is tuned to the specific frequency of light flashes. Flashes of light can be detected even if they are weak, and they are less susceptible to ambient lighting and reflectivity of objects. These are used in most IR remote control units. So, here you see these are the flashes of lights, and this edge is corresponding to LED on and this edge corresponds to the LED off. And you can see there is a time of 25 microseconds between two pulses. So, this results into 40 kilohertz of flashing frequency, and this receiver, this senses the pulses. So, this is the transmitter and this is the receiver circuitry. So, this demodulator is detecting, this can be either active high or active low detection. So, till the flashes are coming, those are detected. When there are no flashes, they are not detected. So, there are two different logics, one is positive true logic or negative true logic, and this depends on the output stage of the electronics that has been used. It can be either open collector or push pull, etc. So, we are using IR analog sensors, which consists, the transmitter consists of a modulator which is shown earlier as of the flashes, and those modulated signal, those are further amplifier to reach to a large distance, and this is a receiver assembly wherein photodiode is used, amplifier is used, there is a limiter, band pass filter, demodulator which is tuned again to the transmitted flash frequency. Then there are integrator to check for the levels of the reflected light and then integrate them. Then there is a comparator, and this is the output stage. So, as said, transmitter consists of modulated IR LED and amplifier. Detector module is built in, it has modulation decoder or demodulator. Detection range varies with different objects. White surfaces has 90% reflectance, while grey surface has 19% reflectance. And because of this packaging and shielding and other control electronic circuitry, these sensors are insensitive to the ambient light. So, which is a major application or quality we can say. There are various issues while considering the sensor, selecting the sensor, and calibration is one of the major issues. Sensors can exhibit non-ideal effects, there can be an offset. Suppose the offset may change with respect to the ambient light. Non-linearity also can be seen, output may not be linear over a certain range of distance, then there can be a cross parameter sensitivity such that secondary output variation also is affects the signal. Calibration is adjusting output to match the parameter. Then there are various methods: analog signal conditioning, lookup table, digital calibration also can be done with the, suppose that the environment is highly susceptible to the change of temperature. Then compensation methods are used to remove secondary sensitivities. These must have sensitivities characterized and can remove with polynomial evaluation. So, all these factors are taking action or answered in the package which is highly integrated. So, in the experiment in the Center for Mechatronics, we will be performing experiments by using digital sensors. So, we are using 4 digital sensors to drive a PET robot. Then we will see another experiment, IR range finder distance measurement sensor. So, this is a break beam sensor. This you might have seen while covering the theory on sensors part. These kind of sensors, as I said earlier, those are used in the encoders. So, these work in the direct mode, and this is again a digital sensor which works in the reflective mode. So, here you can see the package of the IC, and this is the package for the direct digital sensor, this is the package for the reflective sensor. And many a times this is the basic design of the infrared proximity sensor. So, this is a LED which is biased through this resistance and then connected to a source. This emits light, and this is a photodiode. This sends the radiation in the IR range, and this changes its output. So, here you can see the responses. So, this is a digital kind of thing. So, whenever some object passes through this, intrudes through this sensor, passes in between the, breaks the beam, then you can sense the signal. And these are more sensitive to ambient light. So, if ambient light increases, the bias voltage changes. So, here you see a digital sensors usage for making a simple PET kind of robot. We are calling this as a PET because this we can, as you will see it in the laboratory, we can take it along with us as a pet or as a child. This is implemented, this package robot is implemented by using 4 IR digital sensors. These are commercial and of Pepperell plus Fuchs company. They are nicely packaged, so the ambient light effect is reduced. We are using 1 SPDT and 3 DPDT relays to achieve the control of the robot, and 2 motors are used. Here you can see these 2 motors are used to drive the robot. We are using a battery pack for the voltage source. So, as you see, so there are 4 sensors. This is a forward sensor, this is a left sensor, this is a right sensor, and this is a power on sensor. So, and here is the truth table as for the working of this robot. So, as you see, whenever the power on source is off, and even if any of the sensors or all of the sensors they activate, the robot is halted, none of the motor is activated. And when the power on sensor is activated, the default motion of the robot is forward, because both the motors, left and right motors, they are made to move in the same direction, in the forward direction. So, we see for activation of the robot, you need to have this power on sensor always on. So, this we are calling it as a accompanying function kind of. So, you see this is the truth table. So, when forward sensor is activated, the robot will start moving backward till it goes out of the range of that obstacle in the forward, and then again it will resume its forward position. When the left sensor is activated, the robot will start going in the right, it will take the right turn, and for that a differential drive method is opted. So, while taking the right turn, the left motor will be moved in the forward direction and the right motor will be off. And when two or more sensors they activate at a time, excluding this power on sensor, the motor will have a confused state. So, it will make tuck 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 sound. So, we can avoid this state of the motion by using a KMAC for above truth table, and a digital circuit can be designed which can avoid this jumble state. In the second experiment, we will be using this OCD 5000 Pepperell and Fuchs sensor and receiver assembly. This is an analog distance sensor. This works at a 880 nanometer frequency wavelength, and the rated voltage is 10 to 30 volts, and there are few resistances which are needed to make the sensor operate. So, we have connected 3 resistances as shown here. Output is available at pin number 4 with respect to ground, and it takes around 200 milliseconds of time to have the output displayed. We will be using a multimeter for reading the voltage, and in the laboratory we will perform the experiment by using a white reflective surface. We will take the readings at different distances, and this sensor, it works till 5 meters of distance. Here we have taken the readings up to 250 centimeters, and you see till this region it is very linear, and later on it changes its response. So, one can have a lookup table of the readings, or one can plot a graph and check for the readings. So, this sensor can be easily interfaced with the data acquisition cards. So, these are the 2 experiments which we have seen and which we will be carrying out in the laboratory also. So, my special thanks to Mr. Rajendra Kumar Rai for his assistance in setting up the experiments, and thanks are also due to the staff at Center for Mechatronics and Media Lab.